So we're moving on to electric circuits, which is chapter 30 and 31. The way Knight does it is 30 is more conceptual and 31 is more quantitative. So now we're going to start with the more conceptual. And we've already dealt with an electric circuit. We've talked about this a little bit. Here's the capacitor. So the capacitor has this negative side and the positive side. And when you hook a wire up, the electrons on the negative side leave, and then electrons come to the positive side and cancel it out. All right. And this process is an electric current. So electrons are moving through the wire, which is just a conductor. And so here's our model of a conductor. We've talked a little bit about this before, but the conductor has these positive protons, and then the negative electrons are moving around, and they're free to move around. And so these electrons are the charge carriers in a metal. And that's what we're focusing on a lot today. And so here's a picture just of the life of an electron for a little bit. And you can see that it's moving around and it's bouncing off of these protons, but it doesn't really go anywhere. It's just sort of hanging out. And so that's where our battery comes in. So our battery, our EMF, okay, and we'll talk about how this works, but it essentially sets up an electric field in the wire. And one part that's a little bit confusing is that this electric field, okay, because it's electrons move opposite the electric field because they're negative. But anyway, so if we add an electric field, then look at the lifetime of the electron, okay, it slowly moves to the right in between its bounces because of this electric field, all right, and we call this the drift velocity. And the analogy I like to use is this thing called Plinko, which is a game from the game show Price is Right. And the way this works is it's a little board with little pegs in it. So the pegs are kind of like the positive protons, and the board is inclined. Okay, so if you look at a side view, it's got some angle. Here would be the pegs, and then the little discs, here's like a little disc, are the sort of like the electrons. And so the contestant would drop the disc in, and the disc, because it's inclined, would bounce through these protons and eventually hit down the bottom where they would win a prize. And so basically the little pegs are like the protons and the angle is like the EMF. Okay, so it's sort of like, or even better yet, the angle is sort of like the electric field. Okay, so how much the electrons want to get through. And so here's a picture of this discharging of the capacitor. And so we talked about this a little bit last time, like our capacitor lit up a little light bulb or something. And so you got negatives and positives. Now the one thing is that the velocity here of these electrons is really small. It's like 10 to the -4 meters per second. But as we'll see in class, or as we saw in class, when we discharge the capacitor, it's really quick. Okay, so what's happening? Well, here's what's happening, and Knight talks a little bit about this too. But so on the negative side, there's a bunch of negatives here, and the positive side is the protons that are bare because the electrons have left. And so the electrons do move really slowly. So they move maybe just a little tiny distance here. But what they do is they move every other electron over. Okay, so these electrons that were in this little space here move up and cancel out these positives. Okay, and so even though they move really slowly, they move all the electrons in the wire, so the effects of what they're doing are pretty quick. And so it's just like at home when you turn the light switch on, all right, the electrons are moving slowly, but they turn the light bulb on pretty quickly. Now Knight talks about this, and this is a really important idea too, okay, similar, another kind of an analogy. If I'm pushing a book across a table with some force, okay, friction is going against me. I got to keep pushing to keep that book moving. It's the same thing with electrons. Okay, the electrons are feeling a frictional force because they're bouncing off those protons and stuff, and so the battery needs to keep this electric field up in order to keep that push going. And so the battery, we call this the electromotive force, and it's the potential difference that's given to your circuit. Again, for like a car battery, the electromotive force is 12 volts. Here's the symbol we would use in circuit diagrams. So there's a big N and a small n. The big N is the positive, the small n is the negative, and we use the script E. So this is what's responsible for the electric field in our circuit. And so here's a picture. Now the book likes to do stuff like this, so here's just an example. Here's literally just two batteries put together, but it counts as sort of one battery that's twice as much. And so when you put two batteries in to say you're into something that you're using like a flashlight, okay, that's what that would mean. And what happens is in the battery there's a bunch of electrons here that want to go around and get to the positive side. And so they get out and they push other electrons, and what happens is you end up having this electrical current that in this case would go counterclockwise. Okay, and we've been talking about this, but now we're trying to define electrical current. And here's the actual letter for electrical current. It's I, and it's the change in current over change in time, and the units are the ampere. And if we just make a little wire here, all right, and we make some sort of, so here's like a little cross-sectional area of the wire. All right, the way this works is the current is how much charge passes through that area per second. Now one thing, and this is all Ben Franklin's fault, it's a little bit tricky, is that when he named the charges, he didn't know which ones were the ones that were actually moving. So the ones he called electrons that we know now are the ones that are actually moving, okay, go counterclockwise through this picture I have here. And so we call that current the electron current. Now, a lot of times, especially in chapter 31, we'll think about it as positive charges actually moving, and they would, in this picture, positive charges would move clockwise. Now it's the same thing, positives going clockwise is the same thing as negatives going counterclockwise, so it really doesn't matter, all right, but it's nicer to talk about electrons when we're dealing with conceptual stuff, and it's nicer to deal with positives when we're dealing with actual numbers. Now here's the same capacitor setup that we had before. So here there's a bunch of negative charge, you can see it's established here, and then here there's a bunch of positive charge. And like a conductor, it just goes to the outside and it's all distributed uniformly. All right. Now as soon as we connect those wires, what happens is the charge redistributes itself. And it redistributes itself, so it's got an electric field pointing through the wire that's constant, and that keeps the electrons moving. Again, electrons want to go opposite that, and so the electron current would go again counterclockwise. Notice right here there is no charge at all. Okay, it's a neutral. So this is tricky to understand in every situation, but it happens, and this is what's responsible for the motion of the charges. And so here's a little picture. We can look at this, for instance, right here. Okay, the electric field, this is a big amount of positive charges there, a small amount there, so overall, electric field will point that way. Right here, there's some positives here, some negatives, overall it points that way. Everywhere in this wire, the electric field points to the right, so if I was an electron, I would want to move this way. Okay, so it's important to make sure this makes sense to you. So let's stop here, take a pause, and figure out, so here's a wire with some charges on it. Which way would the electrons want to flow in this wire? Okay, so with this one here, hopefully you got that the electrons want to flow to the left. And let's look at 2 points. Look at this point right here. All right, if I'm right here, okay, there's an electric field from those 4 positives that points that way. It's pretty big. Now there's electric field from those 3 positives, but it's pretty tiny. Okay, so overall at this point here, and if we figure that these guys are too far away, they don't matter, overall the electric field is going to point this way at that particular point. And if I look somewhere over here, okay, now this positive charge is going to push to the left, but really tiny. Those 2 positives are going to point that way, but a little bit bigger. And if I again assume that these 2 charges anyway, those charges are going to be pointing that way anyway, overall the electric field points this way. Okay, so you want to be able to convince yourself that in that wire, the electric field is always pointing to the right, which means electrons will go to the left because they go opposite the electric field. All right, so dealing with the resistors, which we've been talking about resistors. Wires are resistors, okay? Any electrical device will resist the flow of current, and our equation for that is right here. So the resistance equals these things. There's the resistivity, which depends on the material and is basically how many of those proton bumps the electrons got to get through. Then there's the length of our stuff, and then the cross-sectional area. And here's a little picture. So length and then cross-sectional area would be right here. And we can talk about this a little bit conceptually in terms of our Plinko board. So if I have one Plinko board, if I add another one, all right, and make it longer, all right, so what happens is then it's harder for the electrons to get through. So they got to get through twice as many of these little bumps, okay? And so if I increase the length, I have to increase the resistance. Now, similarly, if I take a Plinko board and add one parallel to it, all right, so what I'm doing is I'm kind of increasing the total area. All right, that means if I have so many Plinkos here, I can add more over here, and I get more chips coming through. So I reduce the resistance. Okay, so if my area is increased, the resistance is decreased. Hopefully that makes sense conceptually. And our big law that kind of ties everything we've been talking about together here for resistors is Ohm's law. All right, and it's officially written out this way here, but I kind of like it better this way. So this is the current, right, the actual current, and it depends on the voltage divided by the resistance. Now resistance is going to be measured in units of ohms, which we have right there. And basically the way this works is higher voltage, higher current, all right, higher resistance, lower current. And hopefully that makes sense to you here. So if we look at this little equation right here, if I have a higher potential difference, which means essentially there's the battery really wants it to get through, okay, I'm going to have a larger current. However, if I have a higher resistance, it's harder for the electrons to get through, and so I have to have a lower current. And so this is kind of an equation form that describes most of what we've been talking about today. A resistor, so again, it's a device that resists current flow, and our resistor looks like this right here when it's in the circuit diagram. And one thing that we should spend a little bit of time on, which when we get to circuits, is that wires are resistors, but they have really, really tiny resistance. So the resistance of a wire is way, way smaller than the resistance of the resistors we use. And so even though it's a tiny bit of resistance, we can pretty much forget about it. All right, and here this is Knight's version of that slide. It's basically the same idea. Okay, that resistors of wire, the resistance of wires is so tiny that we can pretty much forget about it as far as talking about resistances. And the last thing we're going to talk about is our other Kirchhoff's law. So we've talked about one already. Here's the other one. It's basically the junction law, and it says that the current going in has to equal the current going out. Okay, and I like to think about this as sort of like a little highway. Okay, so if we have a little highway of breaking off here, okay, if I have like 3 trucks coming in and 2 trucks go this way, I know that 1 truck had to go that way. It's the same idea. The current coming in has to go somewhere. Okay, so here's a problem with this guy. If this makes sense to you, then you're pretty much set with this. But here we've got 4 wires with 3 currents. What's the 4th current? So pause and give this a try. Okay, hopefully you got 2 amps to the left, all right? And if I do this, so my current in equals my current out. Okay, so if I look here, the current's coming in, there's a 2 amps coming in, all right, and plus a 5 amps coming in. Now if I look over here, the current coming out would be 9 amps. I'm just going to guess that the current coming out in my last wire, okay, the 4th wire is coming out. Okay, but I could be wrong, so who knows. And so here I get total of 7 amps, and this equals 9 amps plus I to the 4th. And if I go over to here and keep working on this, you'll see that my I to the 4 will equal 7 amps minus 9 amps, which equals negative 2 amps. So my guess was wrong. The good news is, though, the equation is smarter than me, and it was able to tell me that I was wrong. And so it's saying that it's 2 amps, and so actually not, instead of being an out, it had to be an in. And so it's 2 amps going to the left would be the one that has to be there.